In this video, I'm going to talk about clustering and different approaches that the clustering is done. And clustering is a major category of unsupervised learning. Let's do a bit of recap. What was unsupervised learning? If you remember, supervised learning was when the human effort was involved, and unsupervised learning was when no human effort involved. In short, basically, because we have some labeling when we are dealing with supervised learning and its data, then human needs to put some input when we're dealing with those problems. But when we're talking about unsupervised learning, basically we don't do any labeling for the data. If we want to look at it from a different perspective, supervised learning could be seen as a learning conditional distributions, PY, probability of Y happening on the condition of X, where X are the features and Y are the classes. Whereas when we are discussing about unsupervised learning, we are only learning the distribution of distribution P of X, where X are our features. Now, let's focus more on clustering specifically. If I want to give you a brief definition for clustering, it could be seen as assignment of a set of observations into subsets so that the observations in the same subset are similar in some sense. And this similarity at this point is quite broad. We don't have any predefinition at the moment what similarity is, but basically we want to group things that are similar to each other considering some specific measure of similarity. So why clustering is an approach to consider? Unsupervised learning, classification, regression is most talked about comparing to clustering. But clustering is also something very useful, and there are some reasons for it. First of all, labeling is expensive. When we're dealing with supervised learning, we need to have labeled data, and it's not always feasible to do the labeling. So one reason that we would like to do clustering is that labeling is expensive. Another one is that we could gain useful insights into the structure of the data that we are working with. So it is some sort of exploration, if that's a way to consider it. Basically, we are given a data set and nothing more about it. Clustering will help us to get more perspective. In the same time, on the same line, we could find prototypes in the data. So clustering could provide useful insight for us. And what is the goal of clustering? Let's imagine that we are given a set of data points. You see many data points on these figures, and each described by a set of attributes. In this example that you're seeing, we have attribute F1 and attribute F2. And the idea is to find clusters such that the inner cluster similarity is maximized. Basically, what I mean is that the points that are closer to each other have the most similarity to each other, and intra-cluster similarity is minimized. So basically, if we take a point from cluster 1 and 1 point from cluster 2, they have least similarities to each other. That is why they are separated. And as it is obvious, for doing that, we require the definition of similarity measure, which we are going to get to at some point later during this video lecture. But before moving forward, there is something that I want you to be aware of. That is something called clustering bias or clustering illusion bias. And by that, I want you to pay attention to this point that humans generally tend to see patterns in what are completely random outcomes. In other words, it is in our nature inclination to create order from chaos, even when there is no order there. For example, as you see in this figure, Monte Carlo casino event is an example of clustering illusion bias for individuals who were present during that night. The thought process was that since the ball had landed on the black so many times, it was bound to fall on red soon. And the outcome of that specific roulette game is the outcome of a roulette game is an independent event. Whether or not the ball hit black or red does not indicate what the ball will hit next. And if gamblers see patterns where it doesn't exist, eventually they're going to lose a significant amount of money betting against, for example, in this scenario, against black, because they were sure that the black and red outcomes had to even out, but this is not always the case. So we need to be careful dealing with these clustering biases when we are doing clustering methods or algorithms. Another thing about clustering is the perception we have about it. In the example here, you see some sort of clustering done on Netflix data, and unlike what we probably have in mind, because we see as clusters as isolated spaces, it is more a continuum than a discrete clusters, as you see in this example. And if I want to say some other points about the things that we need to be careful when we are doing clustering, is that probably we are using clustering more than it should be, because people generally assume that there is an underlying domain with discrete classes in it, but in reality the underlying data is usually continuous, just as what you're seeing here with Netflix. Continuous models like dimension reduction or k-nearest neighbor tend to do better. So now that we discuss about what clustering is, why we need to do clustering, and what we need to be aware of and careful about when we are doing clustering, we're going to see some categorization of clustering as well. We could considering clustering to be hard or soft, and when we are saying hard clustering, basically we specifically decide that the same object can only belong to one single cluster. But when we are talking about soft clustering, same object could belong potentially to different clusters. So this is one categorization of clustering. Another one is we could have either flat clustering or hierarchical. And as the name suggests, when we are talking about flat clustering, the clusters are flat, and in hierarchical clustering, the clusters form a tree shape. So the question now we need to answer is that how to cluster an unlabeled data set that we are given, and how to find similarities. In a sense, similarities is hard to define, but at the end we know it when we see it. And another thing that you need to keep in mind is that clustering is quite subjective. So doesn't mean that when we are doing clustering on one single data set, two different modelers, two different people will get the same outcome. We could still get clustering that is useful from one person to the other, but there is no guarantee that they are doing the clustering the same way. For example, in this Simpson example that you have, we have here we have the Simpson family as a cluster and the school employees another cluster, which is totally reasonable. But we could also cluster them based on their gender, females or males. So talking about all these things, it is obvious that we need to define some sort of similarity measure, and let's say what kind of characteristics the similarity measure should have. And let's start by defining a similarity measure in the sense that if we have two objects, for example O1 and O2, from the universe of possible objects, then the distance between two object O1 and O2 is a real number denoted by d of O1 and O2, basically distance of O1 and O2. So this is one of the first things we need in defining similarity measures. We need to know what does it mean when we say something is close to each other, to the other thing, or the two things are far from each other? So the definition of distance function, distance of O1 and O2, the distance between two objects O1 and O2, is important. And if we have such a measure, then we could start basically calculating that distance function. And I'm not still giving you any specific function, but for example, these two animals, we could say based on some distance function are close this much. When we are talking about Peter, two different names, basically different languages, the same name, we could, for example, count the letters that are similar in both PTR, and then we say 3. Or we could have a measure for fingerprints, which, for example, in this case, they could potentially be very close to each other, and then a large value shows the distance. So these gray boxes is basically our distance function. We feed in two objects, two data points, and the output is a distance value that we could use when we are doing clustering. So this distance function, what property it should have? It should have 4 different properties. It should have symmetry. Basically, we should have the distance between A and B is equal to distance between B and A. We should also have constancy of self-similarity, and that means that there is no distance between the same object and itself. We should also have positivity or separation, which means that there is only one condition, that the distance between two things is 0, and it is where those two things are equal to each other. If this is not the case, there will be a value that shows the distance. We should also have triangular inequality, and basically if you have a triangle of 3 points A, B, C, the distance between A and B is always either equal or smaller than the sum of distance between A and C and the distance between B and C. And there is some logic in having these requirements set in for our distance function, and we're going to go briefly through them and say what is the intuition before requiring such measures. First of all, let's discuss symmetry. Distance between A and B equals distance between B and A, and it makes sense because if not, we could claim, for example, Alex looks like Bob, but Bob looks nothing like Alex. At the same time, we had another another measure that was important for us, and that is the constancy of self-similarity. And if that does not hold, it means that you could claim Alex look more like Bob than Bob does basically look like himself. And there are two more characteristics that needs to be satisfied. First is positivity. Basically, we are saying that if distance between two things are 0, if and only those two things are equal, and if not, basically there are objects in your world that are different, but you cannot tell them apart, so this is not good. Your measure should be able to do that. And finally, the triangular inequality, if it doesn't hold, basically what we could claim is that Alex is very like Bob, Alex is very like Carl, but Bob is very unlike Carl, which doesn't make sense. So this is why we need all these requirements behind the measuring, the distance functioning. If you remember at the beginning of this video lecture, I said that we could have one way to categorize clustering is whether to consider them as hierarchical clustering or flat clustering. And the first thing that we're going to discuss is about flat clustering and hierarchical clustering. And when I am saying hierarchical clustering, basically we create a hierarchical decomposition of the set of objectives or objects using some criterion, and flat algorithms constructs various partitions and then evaluate them by some criterion. And in hierarchical algorithm, we use dendrogram. That is a useful tool for summarizing similarity measurements. And the similarity between a dendrogram is basically represented with the height of the lowest internal node they share. For example, if you see these two, the height is much higher basically when you are considering something in this cluster and this one. Hierarchical clustering can sometimes show patterns that are meaningless. For example, in this example that you're seeing here, the tight grouping of Australia, Anguilla, St. Helena, etc. here basically could be considered quite meaningful because all these countries are former UK colonies. However, when you get to right side of this dendrogram, the tight grouping of Niger and India here basically does not make much sense because there is no connection between these two. So we need to be careful when we are interpreting the result of a dendrogram. It's not necessarily always meaningful. We could always look at the dendrogram to determine the correct number of clusters. For example, in the examples here, you clearly see we have two large clusters. Of course, it matters where we are drawing the line, but for example, when we are only seeing here and drawing the line here, then we can see obviously two clusters, and this is also the same data represented here. So this is one of the usefulness or useful points of the dendrogram. It's help us just by looking to see how many clusters we are dealing with. Another potential use of a dendrogram is detecting outliers. Here you see in the plot we have one outlier here and here. In this graph, basically this one is the outlier. It doesn't belong to the main clusters that we see here. And since we are talking about a hierarchical cluster, there is one thing that we need to keep in mind is that we cannot always test all possible trees. So we will have to heuristic search the possible trees, and we could do it two ways. We could either do it bottom up, basically meaning that starting with each item in its own cluster, each item one single cluster. Then we find the best pair to merge into a new cluster, and then repeat until all clusters are fused together. Basically, every data point starts individually, and then step by step we just start merging them together until we could not find any reasonable iteration to have fewer number of clusters. There is another way of doing that, and that is top-down clustering, divisive clustering. Basically, it is just the other way around. We start with all the data in one single cluster, then consider every possible way to divide the cluster into two, and then we choose the best division and recursively operate on both sides until we get where we want to get. Okay, so where we need to start? Let's go back to our Simpson examples. We begin with a distance matrix. Whatever distance function that we have defined, this is where we are going to use it. So we begin with a distance matrix, and then which contains the distance between every pair of objects in our data set. For example, here the distance between these two is 8, and the distance between these two is 1, as you see. Okay, now let's see how we want to do this bottom up. This is an example of bottom up clustering, and what we're doing here, as I said before, we are going to start with each item on its own cluster, and then we choose the best. I am skipping the one that everyone was sitting in one cluster, and then I'm showing you the all possible merges. These two, these two, these two, and my distance function says basically this two is the best cluster that I can get here individually. And then I'm going to iterate. Basically now, having all these, now these two are one cluster and all the other ones is still single point clusters. Which one is the best option? And then I see that I can have two more clusters here. And we continue this until we get the clustering that we want. So this was a bottom-up clustering. So until now, we know how to measure the distance between two objects, but what about distance between an object and a cluster, or definition of the distance between two clusters? And I'm going to give you some definitions here. For example, single linkage or nearest neighbor. In this method, the distance between two clusters is determined by the distance of the two closest objects in the different clusters. So what we are doing here, we go into clusters, find two objects that are closest in these two clusters to each other, and then we find the distance. We use the distance function, and that is how we are calculating the distance between two clusters. Basically, we are calculating, as I said, the distance between two nearest neighbors in two different clusters. We could also do just the opposite, complete linkage, which is the furthest neighbor. And in this method, the distance between clusters are determined by the greatest distance between any two objects in the different clusters. And by that I mean the furthest neighbors. We could also have group average linkage, which in this method the distance between two clusters is calculated as the average distance between all pairs of objects into two different clusters. Okay, now the question that is raised here is that we said that we have two different methods of hierarchical clustering. It could be either bottom up or top down. And we have three questions that we would like to answer. Which one is the most complex one? Should we go with bottom up or top down? Which one is the most efficient one? And which one is the most accurate one? These are the measures that we want to know when we are starting using an algorithm. Of course, we should always keep in mind our computational resources, the time that we have, and how any of these is important for us. So let's start answering them one by one. Which one is more complex, bottom up or top down? And the answer is top down, because a flat clustering is needed as a subroutine in each step, so it takes more computational power in a sense to do that. So if we are going for something very easy and fast, probably it's better to do bottom up, as the example we saw just before these slides. What about the more efficient one? Well, top-down is the most efficient one of two, and the reason is that for a fixed number of top levels, using an efficient flat algorithm like k-means, divisive algorithms are linear in the number of patterns and clusters. And agglomerative, basically bottom-up algorithms, are least quadratic. So if you're going for more efficiency, top-down should be our choice. And finally, which one is more accurate? The answer is again top-down. Bottom-up methods make clustering decisions based on local patterns without initially taking into account the global distribution. These early decisions cannot be undone. So if you made a decision, let's say in the first couple of stages, you just cannot go back and say, no, now I realize that they're not good enough. We need to stick with whatever decision that we had made, basically. And top-down clustering benefits from complete information about the global distribution when making top-level partitioning decisions. And this all boils down to exactly this last point, because in the top-down clustering, we basically have everything in one single cluster, and only then we start dividing, whereas in the other way around, everything is sitting into one single cluster, and it is very possible that we could not see one general pattern when we see individual points as individual clusters. So if I want to give you a summary of these three questions, probably top-down clustering is the one that you should stick to if you have a project that you want to be accurate and efficient, and you have enough computational resources. So complexity is not an issue for you. Let me give you some final footnotes about hierarchical clustering methods. First thing is that in the hierarchical clustering method, you don't need to specify the number of clusters in advance, and that is already something good. So it requires minimum involvement. Hierarchical nature maps nicely onto our human intuition for some domains, but there is this problem with hierarchical clustering as well, that they do not scale well. Time complexity of at least time complexity of at least n to the power 2, where n is the number of total objects, is the complexity that we're going to get. And like any other heuristic search algorithms, local optima are a problem. And, and finally, interpretation of the result is very subjective. Okay, now we know some information about hierarchical clustering. Let's talk a bit about flat clustering as the opposing method to the hierarchical clustering. And as it is obvious from the name, this is the type of method that is non-hierarchical, and each instance is placed in exactly one of the k non-overlapping clusters. As you see here, basically, this is a clustering that you saw earlier based on the gender, females and males, and there is no overlapping, at least in this example, between them. Uh, and uh, basically, I'm going to give you one of the popular methods when it comes to flat clustering, and that is k-means. And it has 5 different steps. The first step is that you decide on the value k, basically the number of your clusters that you think there should be. So this is already something that you don't know before, and you do a bit of guesswork, or you have something in mind and you are interested in this number of clusters, but you could always go back and decide with different values. After that, we need to initialize the k cluster centers, and by that we pick k points and say these are our cluster centers, and this could be done even randomly, so don't be so fussy about them. Don't try to visualize and they think this is probably the center of this cluster and that cluster. Don't overthink it too much. And then we should decide on the class membership of the n objects by assigning them to the nearest cluster. Now, basically by this, I mean that we have the center of cluster, we see what are the closest point around that center rather than the center of another cluster, and then we assign objects to the clusters. Then again, we go back and re-estimate the k-cluster center that we put at the beginning by assuming the membership above are correct. And if none of the n object change membership in the last iteration, we exit. Otherwise, we go back and again change the membership of the objects that we have. So we iterate until the time that we don't see any changes and we stop there. Now I'm going to give you an example of a k-mean clustering, and the distance metric that we're going to use is Euclidean distance that you have already seen before. These are the objects that I have here, and I want to do some sort of clustering, and the first step is to decide on the k. I assume that I have 3 different clusters, and I initialize k cluster centers. You see, I mean, they're quite random. I really didn't think where to put them. And then we decide on the class membership, and I thought probably this is the best clustering that I could find at the beginning based on my distance measure, Euclidean distance at the first step. Then when I have this cluster, then I think this is not the center. Here, the center should be moved here. For this cluster, the center should be moved here. And for this one, the center should be moved here. So I change my centers. And then I iterate until I get where I want to get. And now I think I have my clusters here, here, and here. I have my 3 clusters. So this was k-means simply put. So let's discuss about the final notes on k-means, basically its strengths and its weaknesses. The strength is basically its relative efficiency. It is complexity is O of tkn, where n is the number of objectives, k is the number of clusters, and t is the number of iterations. And normally k and t, which is number of iterations, number of clusters, is much smaller than the number of objects. And it often terminates at a local optimum. Basically, it terminates where we could relatively be happy with. But then it has some weaknesses as well. First of all, it is applicable only when mean is defined. But what about when we are talking about categorical data? How we are going to do k-means with categorical data? We also need to specify k, which is the number of clusters in advance. This already means either we need to have a bit of knowledge about the dataset that we are working with, we need to have some pre-assumptions that what are going to be my clusters, or we need to toss a coin and be cross fingers that we're going to get a good clustering out of that. And unfortunately, it's unable to handle noisy data and outliers. And it's also not suitable to discover clusters with non-convex shapes. So if I want to wrap up the flat clustering, these are the things that you need to keep in mind when we are discussing flat clustering. First of all, we need to select features to characterize the data. Then we need to collect the representative data, and then we need to choose a clustering algorithm, and finally we specify the number of clusters. These are the backbones of any flat clustering algorithm that we want to implement, basically. There are some bottlenecks into flat clustering. First of all, it is difficult to find true clusters. We could have irrelevant and redundant features. We could have also the points that are equally close. Then making a decision there will change the cluster from one to the other one, where basically more or less there is no logic or reasoning behind that. So these are the problems that we have. But there are some solutions for these bottlenecks. One solution is basically dimension reduction. Instead of keeping all irrelevant redundant features, we could simply focus on the feature subset selection. We could use a set of meaningful features to work with. We could also do cluster ensemble using random projections, solving the problem of all points being equally close to each other. Sorry. There is one thing that we need to consider as well, is the curse of dimensionality as well. And when I say curse of dimensionality, it sounds something out of Harry Potter movie, for example. But what it really refers to is when your data has too many features. You have already seen it in the bottlenecks of the clustering approach. If we have more features than observation, then we run the risk of massively overfitting our model. And this would generally result in terrible out-of-sample performance. When we have too many features, observations become harder to cluster, and too many dimensions could cause every observation in the dataset to appear different from the other ones. And because clustering uses a distance measure, like Euclidean distance as you saw, to quantify the similarity between observations, it becomes a big problem. If the distances are all approximately equal, then all observations are equally alike, as well as, of course, equally different, and then no equal cluster can be formed. And this is what I already explained in the previous slide. The way out of this is basically to use dimensionality reduction. So now you have a brief understanding of what clustering is, what clustering approaches we have. As you said, we could have we could have different categorization, we could have hierarchical clustering, we could have flat clustering, we could have hard clustering, we could have soft clustering, and even, for example, within hierarchical clustering, we could have top-down clustering or bottom-up clustering. So there are so many different ways of doing clustering, basically. And since, as I already mentioned, labeling could be expensive and you probably don't have any pre-knowledge about your data, clustering is and could be a good method to use when you want to get an understanding of an unstructured data that you have. In the next video, I'm going to show you a couple of examples of how clustering could be done in Python, and we are going to see one example of hierarchical clustering and one example of k-means clustering. So for now, I close the video here and I see you in the next video.